And as my fellow colleague Alexander mentioned, like a cherry on the top, I would like to welcome Mark Brown from Microsoft. Good morning, Mark, and welcome.
Hi, how are you? Good evening to you, I guess, right?
Yeah, late afternoon. Hopefully we didn't need to wake you up too early like we did with your colleague.
No, it's nearly 9 a.m. here, so I've been up for a few hours already.
Okay.
Early riser, so lots of calls with customers and folks in Europe. So
Yeah.
it's I'm no stranger to
even during the weekend. They are not letting you go to. Yeah. So if I'm not mistaken, Mark, you are principal program manager for two teams, both Azure Networking and Cosmos DB.
No, I was on Azure Networking a few years ago, but I've been on Cosmos DB for about 3.5 years now, a little more than that, maybe almost 4.
Okay. I was wondering how are you managing both, but if it's just Cosmos.
No, there's no way to manage. I can barely manage one, much less two. So I PM. I manage all of the high availability features, or PM them. So things like our replication and consistency models, multi-master, conflict resolution, and then also PM all of our control plane features. So things like ARM templates or PowerShell CLI, anything that talks to the control plane of our service to provision and manage resources. And then I also lead a team of folks as well, and we're all about kind of driving growth at scale. So lots of customer talks and meetings and partners and community, social media, all that kind of stuff.
Yeah. I may say you're constantly improving the service, so that's great.
All the time. I'm really excited for this semester coming up. We've got some great stuff to announce at Ignite in, what is it, less than 2 weeks now? And then Build is going to be fantastic at the end of May. So really super, we're doing some, I think, amazing stuff. I mean, we continue, even before I was on the team, to do amazing stuff. The velocity of that is continued and will continue. So stay tuned to us and see what we're doing and building. It's, I think, quite remarkable. I mean, the service itself is amazing, I think, which is why I work on the team. I'm super in love with the tech behind building a distributed NoSQL database in the cloud. And hopefully after this talk, everybody watching will be as well. So
I'm sure they will. I will share your presentation as I can see it's ready, and sure. I will leave you on it. The floor is yours, Mark.
Yep, great, thanks. Let me kind of get screens organized here. I'll leave this chat up here, although I may not see questions. So we'll, I guess, maybe do questions at the end for that. Okay, welcome everyone. My name is Mark Brown, and I am a principal program manager on the Cosmos DB team. You can find me quite often on Twitter. I pretty much have that open all day, so you can reach me there, or follow me, or harass me, whichever you like. It's all good. And then our official Twitter handle is at Azure Cosmos DB. Lots of announcements and other stuff through there. If you ever have questions around Cosmos, you can ask myself or our other Twitter handle, which I also keep an eye on there. Okay, so let's get started. We're going to talk about data modeling and partitioning in Azure Cosmos DB. So in today's session, we're going to talk about partitioning and modeling in Cosmos. I really want to help you understand the differences between a database like Cosmos and relational databases like SQL Server or MySQL or Postgres or even Oracle, because there's some big differences between the two. And the point of this talk is to help you understand those differences, but also how to model for it. So I'll work on getting you familiar with NoSQL concepts. And then we're going to learn, or I'll show you, the techniques and technologies used to model data for this type of database, and we'll apply them to a real-world scenario that I think everyone will recognize, I think. Okay, so what is Azure Cosmos DB? Well, officially, it's Microsoft's NoSQL database on Azure. But what we mean by NoSQL is that it is both non-relational and also horizontally scalable. So let's talk about the horizontal scale aspects of Cosmos DB. Unless your workload is very small with just a low number of data or requests, your data is likely to be stored on a number of different physical servers or partitions within something we call a container. Now in Cosmos, we abstract all this away, but under the hood, you're reading and writing data out of Cosmos across a cluster of servers. And this is better known as scale out, and it's how we achieve horizontal scalability by enabling unlimited storage. So when you need more storage, we just simply add more servers to your cluster. This also provides unlimited throughput, as each server that we add into your cluster adds additional capacity to handle requests when you need it. Okay, Cosmos DB is also non-relational. Now, when working with relational databases, you have the ability to define relational constraints between the different entities you're storing. And this lets you define things like foreign keys between entity types and perform join operations across those entity types. Now, non-relational databases like Cosmos don't implement these relational constraints. And you may wonder why. Well, it's because Cosmos is horizontally scalable, and your data is likely going to be spread across a bunch of servers. This could be tens of servers or hundreds of servers, depending on the storage and throughput requirements you need. Now, I don't want to suggest that it's not technically possible to enforce relational constraints across a cluster of servers, but doing so would have an enormous impact on the performance and availability for your database. And because Cosmos is designed to provide predictable performance, we don't provide a way to declare relational constraints on your data. Okay, so is Cosmos DB suitable for relational workloads? Well, yes, it definitely is. In fact, most workloads are relational in Cosmos. You just need to learn to use different techniques to implement the relationships between your entities. And this approach is very different than designing a data model for a relational database. For those that are new to this type of database, you shouldn't follow your intuitions here. Best practices in the relational world don't translate well to this type of database and could even be anti-patterns. Okay, so let's put this into practice. I'm going to spend the rest of this session taking a relational database that anyone who's used SQL Server should know, the AdventuredWorks 2017 database. Well, actually, we'll just take a small piece of this. And these tables represent the canonical e-commerce workload. We've got customer tables. So we've got customer address, and customer password. And then we've got our product tables. So we've got product, product category, and then product tags. And then finally, we have our sales order. So we've got sales order here, and then sales order detail. So with a non-relational document database like Cosmos, there isn't much we can do with this schema as it is. You would never use these tables as is because the cost and performance for trying to perform operations on the data would be prohibitive. Another thing I want to point out too is that in a relational database, the relationships between the data is important for modeling the database. For a NoSQL database, that's only part of the story. What's most important when designing a data model for a NoSQL database are the access patterns for your application. And as I'll walk through this talk, I'll show you the design decisions we make are going to rely on these access patterns to your data. Okay, so a real e-commerce platform, we'd obviously need to implement many more kinds of requests, but this subset is enough to guide our first implementation and illustrate the different design techniques we want to showcase. So here's what our mini e-commerce site will have to do. We've got to create a customer, edit a customer, and then retrieve a customer. We need to create and edit product categories and then list all product categories. We want to also create and edit product tags and list the product tags. We'll need to be able to create a product, edit a product, and then we want to list all products from a category with the name of the category and the tags. We also need, of course, to create a sales order, and then we want to list all sales orders for a customer. And then a couple of interesting queries. We're going to query top 10 customers by the number of sales orders. So this will be like our top best customers. And then we also want to track sales by product category. So we'll have another query to query the total sales for each product category in our e-commerce application. Okay, so let's get started. We're going to remodel this relational database in Cosmos DB. And what we'll do is we'll get started with the customer entities here. So we have 3 tables. And now first we want to translate each table to a corresponding JSON document. Now we could keep these in separate containers in Cosmos, but let's look at the operations we need to support. We need to create a customer and we need to edit a customer, as well as retrieve a customer. Now, given that Cosmos stores data as JSON, another approach we could do is to embed the address and the password tables into our customer table. Now, when I create a new customer, I only need to insert that data into a single container. Reading data, whoops, sorry, moved too far. Reading data is also easier because I only need to read from a single container as well and do it in a single request. Now, I'm going to go into the portal and I'm going to run the queries necessary to get all the data we need for this customer, and I'll show you. All right, so let me go to, all right, so here's my data inside Azure, and I'm going to run a set of queries here, and then we're going to keep track of the cost of those things. So this one is our customer container, and I'm going to fetch this one customer here. So we'll run this query, and here's the customer that came back, and then the query stats on this, we got about 3 RU for there. So let's keep track of that. And then next, we want to get the address for this customer. So we'll run that one too. And here's our address in here. In our query stats, we got about 11 RU. So we're up to about 14 RU so far. And then query 3, we need to get their password. So we're going to run that query again to get that same customer. And there's our password. And another 3 RU. So we had 14 plus another 3. So we're up to about 17 RU. Now, let's look at our version 2 of our customer in here. And I'm going to run that same query I ran before here, exact same one. And I'll query that. And now here we have all of our data. Here's my address embedded in here. And here's my password. And then the query stat, I'm back down to like 3 RU again. So not only did I get all of my data in a single request, but I got it for a very low amount of throughput necessary to get that data. Okay, let's go back to slides. Okay, so now, obviously by embedding that data, all the operations are not only faster, but they're also less expensive in there as well, because I've embedded all that data into a single container. Okay, so at this point, people often ask, well, when would you embed data versus when would you reference it, right? And there's actually some pretty good rules around when would you do that. Generally, you embed data when there's a one-to-one relationship. So this would be customer and password, or what we call a one-to-few relationship. And this would be essentially a bounded one-to-many relationship in a database. And that would be like customer address, for example, because customers do not have an unlimited number of addresses or an insanely high number of addresses. They generally have just a few. You would have maybe a billing address and then a shipping address, or maybe you have your shipping address and then maybe your mom and dad or your sister or brother or some other relatives in there. There's a bounded set of those things. So that's what we call one-to-few. And then the third condition is when the related items are queried or updated together. And that's the case here with our customer data. We are going to typically update or definitely query all of that data at the same time. Now, you want to reference data when there's a one-to-many relationship, especially if it's unbounded. A good example of this would be, say, a blogging platform when you have posts and comments in there. Now, most times, if you have a blog post, you would only have a certain number of comments, but the likelihood of having a blog post where you have a high number of comments is possible, and so you'll want to avoid that. In this case, you want to reference it, so you would add it as a separate row within a container rather than embedding it inside the same document. You also want to do this when you have a many-to-many relationship with your data, and I'll show you an example. Whoops, I'll show you an example of this later, actually, when we model the product tags in our container. And then also when the related items are queried or updated independently. It doesn't make sense to embed data together if you don't use the data at that time. Really, the objective with our modeling here is we want to model the data such that you get the data you need when the application needs it. And so if you don't use that data, it doesn't make sense to embed it into the same document because the size of the document is going to continue to grow unnecessarily. Okay, so because we have that one-to-one and one-to-few relationship between our entities, customer address and customer password, and because we usually retrieve all that data from the customer at once, it makes sense to embed all this data into the same JSON document. Now that we've defined our first entity, we're going to store it in a container we'll call customer. And then obviously when we're creating a new container, we also have to define its partition key. And you may be asking, well, what is a partition key? Well, remember earlier I referred to a Cosmos DB container as an abstraction. Whoops, sorry, an abstraction of over a physical cluster of servers. So when storing documents in Cosmos DB, these documents end up being dispatched to different physical servers. So the question is how do I decide that this document should go to this server and that document to that server? And technically, we're not directly assigning documents to servers. Instead, data is being written to logical partitions. And it's these logical partitions that decide where your data should go to. Now, using the example of a container partitioned by username, we would end up with a logical partition with data where username equals Andrew, and then a second logical partition where data for username equals Deborah, and so on. Now, there's two constraints I want you to keep in mind when you're designing your data model on Cosmos DB, and these are related kind of to the embed versus reference decision. First, each document has a size of 2 megabytes. Now, remember before when I said to embed a reference, it's because each document could be no larger than 2 megabytes, which is why you don't want unbounded arrays inside your documents. Also, the second constraint is each logical partition has a maximum size of 20 gigabytes. So you can't have more than 20 gigabytes of documents where, say, username equals Andrew. Okay. Now, when working with data, we want to strive to achieve an even distribution of data across all of the different logical partitions. If one partition gets a lot more data stored on it than others, this is what we call a hot partition. And we really want to try to avoid that. The same goes for requests as well. If most or all of your requests hit that same logical partition, this is going to be a bottleneck that's drastically going to limit the overall scalability of your model. What you really want to end up with is a design where storage and throughput are more or less evenly distributed across all of your different logical partitions. So the partition key plays an important role in both performance and scalability. Now let's take that example again of a container partitioned by username. If we were to issue this SQL query, you'd notice that it filters on the username property, which is our partition key. And because Cosmos DB understands that, it'll send this query to a single logical partition. And this means that the query is always going to hit one single physical server. So its performance is always going to be good. If we had to filter on something else, say like favorite color, we'd have no idea where the results are going to be. So in this case, Cosmos DB is going to fan out the query to each and every logical partition. And if you probably guessed, this is going to hit each underlying physical server. So this is what we call a cross-partition query. Now, such a query will work, but it's going to have an impact on the latency, throughput cost, and scalability of your application. Now, for small databases or small containers, typically are, well, less than, say, 50 gigabytes, but closer to less than that, the performance impact is not bad. And in fact, you're really not going to notice any impact on your performance or your speed. However, as your database grows larger, this impact is going to become more and more worse because you're going to have to hit more and more servers to answer that same query. Okay, so now with all that knowledge about partitioning, how do we choose the right partition key for our customers? Well, it goes back to the operations that we're going to perform on our customers. We have three things we have to do here. We need to create a customer, we need to edit a customer, and then we need to retrieve a customer. And in this case, we're going to retrieve that customer by ID. So the ID for the JSON documents we're going to store in this container should make for a suitable partition key for our container. Oops, there it goes. Whoops. Where am I? There you go. Okay. Sorry, I'm having some slide troubles here. I want you to note that when we use the ID as a partition key, what we end up with is as many logical partitions as there are documents in the container, with each partition creating or containing only a single document. Now, most users get worried about something like that, but it's actually perfectly fine. Logical partitions are a virtual concept in Cosmos DB. Cosmos is going to co-locate logical partitions on the same physical servers, and then we'll move them to different physical servers when needed. So there's no upper limit to how many logical partitions you can have in a container. Okay, let's get to some code here. So we're going to do a demo. In this demo, I'm going to show you how to query for a customer by ID and then return that customer's data. We'll also show you the throughput that's consumed when you do that query. All right, so we'll get this thing down. All right, so I've got a little Visual Studio project here. And what we're going to do is we're going to query customer here. So I've got my little function, and I'm going to get my database, my customer container. Here's my customer ID. This is the customer we queried for earlier. And then I got a query defined. Here, I'm going to define my query right here. And I'm going to deserialize that into my customer v2 object. In fact, let me show you this. So here is the project, my demos here. And then I have another class that's got all of my entities defined. So I've got a customer class here, customer v2, because I'm going to have multiple customer classes. And then for my array, I have a list of type customer address here. And then I have my password object here. So here's my customer address. I've also got inside customer, I've got a location object here. And that's got my lat long, which is a list of floats in there. And then here's my password object. And then I have other objects too, like my product category, product, which has a list of tags, and then sales order details, and so on. So that's all of my models. And as I go and I get data or read and write data out of Cosmos, I deserialize that into my classes here, into my POCOs. So here, I'm going to create my query, and then I'm going to run the query, and then right here, and then call read next async, and then I'll just for each through that response, and then print out my customer object. Okay, so let's run number A here. And a bit of a cold start, so this is taking a second. And there's my customer object there, right? So I've got the first name, last name, here's the address, and then the coordinates you can see for the address, and then the password, and then the RU charge 2.83. So that's querying a customer, a single customer in there, where I've got a partition key, that's the ID. Now, in Cosmos, there's actually a faster, cheaper way of getting the same data. When you're doing what's called a point read, so I'm querying for a single record of data, and I know the partition key and the ID for the object, you can do what we call a point read. So let me show you that. In my get customer function here, I'm going to do all the same stuff, except instead of writing a query, I'm going to write a function like this, read item async. And I'm going to deserialize that into my customer object. And then I'm just going to pass my customer ID. And then for the partition key, also pass my customer ID. And then I'll go and I'll print that out and show you the RU cost for that. So let's run that one here. That's point read for a single customer. And here you can see, I mean, it came back faster because I've got a warm connection now. But look at this, the request charge for that is just 1. And this is for any data that you read or do a point read out of Cosmos. If it's a kilobyte of data or less, is always going to cost you just a single RU. So this is definitely the most efficient way for reading a single item of data, a single row of data out of Cosmos when you know the partition key and its ID. Okay, let's go back to slides. Okay. Okay, next up, let's look at our product tables. So first up is product category, and we'll do the same thing we did earlier, which is translating this data or entity into a JSON document. And we'll store that document into a new container called product category. Again, we need to look at the requests we need to support in our app. So we need to create a product category and edit a product category. We also need to list all product categories. Now, one thing I want to point out here is when looking at what operations you need to do or you need to support, it's important to know the volume of those operations as well. For instance, we probably aren't creating or editing product categories very often, but the query to list all product categories happens quite frequently. There's another issue here, however, which is there's no where filter on this query. So how do we make this a single partition query? Well, the answer is to use a little trick here that we're going to apply, and we're going to create a new property and give it a constant value in all of our documents. So here I've created a new property called type, and I've given it a value of category. Now I can partition this by type property and then set the value of category in each document. Now, I know you think this is kind of ridiculous and does look a little bit weird, but later on, I'm going to iterate on this design, and you'll see how this actually makes a whole lot of sense. Okay, so in this demo, I'll show you how to query for the product categories, and then we'll measure the RU charge in our app. Okay, so back here, I'm going to list all product categories. So get my database and container. Here's my query, select star from C, where C type equals category. I'm going to create my query here. And then for each through all of my product category objects, and then print out each one. Okay, so run number C. And here you can see I've got 37 categories in here. And it's just got ID, name, and type category. And our RU charge is just a little under 4 RU. So pretty efficient for that. Okay, let's go back to slides. Okay, next up, let's look at product tags. So I'm going to apply the same process here. We'll define a JSON document, and we'll store tags in its own container. We'll call that product tag. And now it turns out product tags share exactly the same access patterns as categories. So we're just going to apply the same strategy here. We'll create a new property called type, give it a value of tag, and we'll set that for each document. Okay, moving on. Let's look at the product table here. First, translate this into JSON. And next, I want to look at the relationship to product tags. Our product table here has a many-to-many relationship with tags. And I need to access tags in my application, meaning that when I display a product, I also need to the tags to display as well. I also need to be able to query for product using tags. Now, I could do this one of two ways. I could store the product info in the product tags table, or I could materialize tags in my product table. Now, given that there are much fewer tags per product than product per tags, it actually makes more sense to materialize the product tags and embed them in my product table. Remember, too, that there's a one-to-few relationship between product and tags. So this, too, makes it a good candidate for embedding. Next, we'll store products in their own container, and we'll call that product. And next, we need to find a good partition key. And again, we'll look at the operations we need to perform and decide on a partition key. We, of course, need to create and edit a product. But the interesting operation here is querying for products by category. This is likely how customers are going to browse and search for products in our e-commerce database. So we need to list all the products that match a specific category. So the corresponding SQL for that would be select star from C, where C category ID equals, say, category A or category B or category whatever, C. And this will return all products for that category. Now, in order to make this a single partition, we would need to have all the products, we would need to have all the products from that same category sit in the same logical partition. So category ID is a good partition key here, and it allows us to store and retrieve all the products in a category very efficiently. But the problem now is that every time I query for products in that category, I get a category ID, and then I get a bunch of tag IDs. But what I really need is to display the category name and a list of tag names in each product. So in order to achieve that, I would first need to run my query to get the products for that category. And then I need to issue a second query on product categories to get the name of the category. And then for each product returned, I then need to issue multiple queries to fetch the corresponding tag names. Now, this will work, but it's not very scalable. And you may be asking yourself, hey, why not just use joins? Well, as I mentioned previously, Cosmos is a non-relational data store, and we don't support joins across containers. data that is modeled in this type of data store is optimized such that it can be served in a single request. So our products table, we're going to need to add additional properties, including the name of the category, as well as the name for each tag that we're going to store. And by doing this, we make sure that we can retrieve all the data we need to our clients in just a single request. Okay, so let's see what this looks like. We're going to add the category and tag names into our product container. So let's go this back to code. So here I'm going to query products by category ID. I'll show you the code for that. Here I'm getting database in my product container. And then here's my category name here, and it's components, headsets. And then here's my query definition here, or my query. And then here's my query definition. And then I'll go ahead and loop through every product for that category here. So let's query products by category ID. And single category. So here you can see category ID, the name, the SKU, the product name, description, and then price, and then also an array of tags with the tag name for each of the products here. And that query cost me just a little less than 3 RU. Okay, back to slides. Okay, so now when we create a new product, we need to populate these additional properties. But what if we rename a category or a tag? How do we manage the referential integrity between the containers? Well, as it turns out, Cosmos DB has a way to handle that, and it's called change feed. Change feed's an API that lives within every Cosmos DB container. So whenever any data is written to Cosmos DB, such as an insert or an update, change feed streams these changes to an API that you can listen to, and then use that event to respond to data that was changed. So in our case, we have to listen to changes that occur to our product category container, as well as our product tags container. And then every time data is updated, it will also propagate that change to our product container accordingly. Okay, so in this demo, I'm going to show you how to use change feed to do that. First, I'll query the product container for a specific category, and then we'll count how many products are in that category. I'll then update that category's name in the product category container, and then I'll show how change feed handles those changes and propagates them to every product for that category. Right, back to this. Okay, so let me show you a couple different things here. We're going to query for products per category. This is just going to give us a count. And then we're going to update that category. So I'm going to get reference to my product category container. And here is my category name, accessories, tires, and tubes. And I'm just going to make a simple change here. So I'm just going to replace the word and put an ampersand in its place. So I'll take my product category here with my category name, category, and then change the name to accessories, tires, and tubes. And then I'm going to call a function called replace item async. This is basically does an update on there, and you pass the partition key, the ID, and then the object that you want to update, basically your POCO, and then that'll serialize that and write it to Cosmos. So that is the update. Next, I want to show you the change feed piece. So here's another project I've got, change feed categories here, and it just has a simple one class in here, my program. And then I'm going to have my reference to my Cosmos client, and then my database, and then product category container. This is the one I'm listening to. And then I have a reference to another container, product, which is the one I'm going to do the update on when I propagate the name change for the product category into the product table. So this is basically just some boilerplate code. I need a reference to a lease container, which is basically provides kind of a checkpoint for the change feed. So it always reads changes, or it knows what changes are new from the last time it read the container. And then I've got a delegate that I create here called input. And then every time change feed detects more changes, because it could be more than one change, it will fire this here. And then you loop through that delegate, that input value, and then you deserialize that into your product category object here. And so for each change to product category that happens, I'm then going to call update product category name. And so let's go down and I'll show you that. So in here, I'm going to query for all products in the category. So I'm passing the category ID in, right? And here's my query. And then I'm going to loop through every product that I queried using that category ID here. And then I'm going to make a count, keep count of how many products I update, change the product category name to my new category name that was passed in from change feed. And then I'm going to call replace item async. So that's the update function. And I'll pass in the partition key, the ID, and then my new product object right here. Okay, so that's it. So here's my main function here. Here's my change feed sitting here running and waiting. So we're going to query products by category ID. Yeah, oh, we already ran that. So let's update product category name. Okay, so now we're going to get a count. I got 11 products that are in this category: accessories, tires, and tubes. Now I'm going to update that, replace the and with an ampersand, and we should see down here in change feed, there we go, one change received. And here we are, updated 11 products with the category name, accessories, tires, ampersand, tubes. Okay. And what we'll do is we'll change it back just so you can see. There we go. Yep, there we are. Now we've reverted it back to the original right there. Okay, that's that. Back to slides. Okay, so now we're on to our last entities, the sales orders. Same process as before. We'll start by creating a JSON document for each of the entities here. And this is obviously another good candidate for embedding because we have a one-to-few relationship. You don't have sales orders where you have an unbounded or unlimited number of items in your sales order, at least not typically. So this makes a good candidate for embedding, and also very efficient because I can use a point read to get an entire sales order with the ID and the partition key in there. So next, we'll store sales orders in its own container. We'll call that sales order. And then let's look again at the operations we need to do here. So of course, we need to create a new sales order. And then we need to be able to list all sales orders for our customer. So our query here is select star from C, where C customer ID equals customer A. So to make sure this is a single partition query, we need all sales orders for a customer to sit in the same logical partition. So we'll make customer ID our partition key here. Now, before we go any further, let's take a step back. When looking at the containers we've defined so far, it's interesting to note that we already have a container that's partitioned by the customer's ID, and that's the customer container itself. So could we store customers and sales orders in the same container? Well, the answer is definitely yes. In fact, not only is this technically possible, it's actually a best practice for NoSQL databases. Cosmos is schema agnostic, so this is something that's totally supported, and it's suitable when data shares similar access pattern and shares the same partition key. Okay, so instead of storing customers and sales orders in different containers, I'm going to put them both in the customer container. I'm also going to change the partition key from ID to customer ID, and I'll also add customer ID as a property to each customer document. Customer documents now will have the same value for the ID and the new customer ID partition key property. Next, to help distinguish sales order and customer entities within the container, I'll also add an additional type property that we saw earlier, and this will have a value of customer for the customer document and sales order for the sales order document, and that'll be in each entity. And this way, I can query for each separately if I want. Okay, so now that we have a customer's container, what we have is a customer container where each logical partition will contain exactly one customer row and all that customer's sales orders. And so now to get all the sales orders for our customer, we simply run with this updated query here. Select star from C, where C.customer ID equals customer A and C.type equals sales order. Okay, so let's see what this looks like here. We're going to query sales orders by customer ID. Oops, let me go back to here. Okay, so we're gonna query sales orders by customer ID here. Okay, so I'm gonna get a customer to my, or reference to my customer container. Here's that same customer from before that we showed a customer or a query on. And here's my query that I showed you earlier in slides. And then creating my query definition here. And I'm gonna deserialize that into my sales order object, pass in my query, my partition key. And then we'll iterate through that to get all the sales orders for that customer. Okay. Query orders for customer ID. And here you can see I've got 2 orders for this customer. Here's the order dates and then the products inside. So there's the sales details inside each of them there. Okay. Back to slides. Okay, finally, let's look at that last request we need to serve. We want to query our top 10 customers based upon the number of sales orders they've had. Now, this request requires you to count the number of sales orders for each customer and then sort those counts in descending order and then return the top 10 corresponding customers. Now, even though customers and sales orders sit in the same container, this is not actually something you can currently do with Cosmos DB's query language. Go slide. Here we go. And once again, the solution here is to denormalize. And this time, we're going to denormalize the count of sales orders into the customer entity. So what we want to achieve is that every time we add a sales order, we also update the corresponding customer document to increment its count of sales orders. And here we can benefit from the fact that each customer and their sales orders sit in the same logical partition. Cosmos DB supports transactions for data sitting or scoped to a single logical partition. So these two operations can be performed in a transaction with a stored procedure or using a new feature in our SDK called transactional batch. And so for our last request can now be served with this query. Select top 10 from C, where C.type equals customer, order by C.sales order count in descending order. Okay, so in this demo, I'm going to show you how you can maintain an aggregate for sales orders in the customer record when a new order is created. I'll then also show you the query for our top 10 customers. Okay, so let's go back to here. All right, I'm going to query customer and sales orders ID here. So here's my customer here. And this is going to be dynamic. I'm using as a type because I'm not distinguishing the sales order or the customer object. I'm going to return all of them. Okay, so I need to put this into a dynamic type when I define my query. And then I've got a customer object here that I'm going to new up, and then new up a list of sales orders. Now, as I iterate through these, I'm going to detect the type. Okay, so here I'm going to detect if this is type customer, then I want you to deserialize me into my customer object. Or if I'm type sales order, deserialize me and add me to my sales list of sales orders here. And then I'll print all of these out. Okay. Next, I'm going to show you create a new order and update order total. So here, get my customer object just like I did before. And I'm going to distinguish that. I'm going to do a point read, and I'm going to deserialize that into my customer object. Next, I'm going to create a new sales order. So I'm going to create a new sales order object here. Add some products to it. And here, I'm going to submit both as a transactional batch. So before I had sales order count, excuse me, on my customer object, and I'm going to increment that by 1. Create my sales order. And then in a single batch, I'm going to call this create transactional batch, pass in the partition key. And then I'm going to call create item on my sales order and then pass that in. And then call replace item, which is basically the update. And then pass in my customer ID and my customer object, which has the updated sales order count inside there. And then I'm going to run that. Okay, so let's run G here. And here is my customer object from before, and then both of their sales orders in here. And here you can see I've got sales order count of 2 materialized within there. Okay. All right, now I'm going to create a new order and update the order total. That's the function I just showed you here. and order created successfully. All right, now let's query for our customer. And here's our customer object. And here you can see sales order count is now 3. And I've got 1, 2, and 3 orders now for that customer. Oops. Okay. I can even show you delete. Let's say this customer says, oh, I don't want that. I'm going to delete it. So you can actually go in here, get a reference to your customer container, and get the customer object. And then I'm going to decrement that by just call sales order count minus, and then call transactional batch again. Pass in the partition key, and then call delete item on the order ID, and then update my customer object, and then execute async. So let me show you that. Here, customer order deleted successfully. And I can go ahead and query for customer and all their orders. And here you can see sales order count now back down to 2. Okay. Back to slides. We're almost done here. Okay. I don't know if you noticed, but that last query was actually a cross-partition query. Now, remember I said before, you want to try to avoid these, but in reality, they're actually okay for operations that aren't run very. Oh, actually, I didn't run that query. Hold on, back to slides or back to code. Hold on. Sorry, I got to give you your money's worth here. So I'm going to show you every demo. So query top 10 customers. So let me go back to that and get top 10 customers. And here we go. Here's our query that I showed you before. And then I'm going to write that back out. Okay, so here, query top 10 customers. And there we go. So here I've got my top 10 customers and their orders in here. And there's my request charge, 1308. And as I kind of let out of the bag, that is actually a cross-partition query, which is why it's so expensive. But this kind of query, it's okay because we're not going to run this query very often. Maybe we run this once a month for a sales contest, and then we send like a gift card or something, a nice note to each of our top 10 customers in there. So for queries like that you don't run very often, it's okay. What's important to keep in mind is that the high volume queries that you're going to run often, very, very frequently, those are the ones that you want to kind of monitor and keep an eye on. It's generally not practical to chase down every single query in your application, and often won't save enough money or throughput to pursue. Really, the key is just analyze the access patterns, highlight those, those top high concurrency operations, and then focus on those. Okay, so in our previous example, we were able to materialize total sales per customer by using the transactional batch, and then save that, and then use that to serve up a query for our top 10 customers. Now, denormalizing data with a materialized aggregate using transactional batch only works when data is stored in the same container as the transactions themselves. However, if we wanted to maintain a materialized view of sales by product or product category, in this scenario, you would need to maintain that materialized view with a different, or you would maintain it with a different partition key. So you need to store that data in a different container and then use change feed to be able to monitor it and maintain that aggregate. So here, I've got this query select star from C, order by C, total sales equals ascending. And this is our sales by category container. And I've got an ID, category name, category sales. So here what we're going to do is we're going to monitor the customer container for new sales orders, and then we'll maintain that aggregate, and then we can run this query. So in this last demo, I'll query for total product category sales, create a new sales order, and then update the total sales by category, and then query for new product category sales. Okay, so this one, I've actually got a different change feed, and it's already been running because I've been creating orders in here, and you can see. So here's what I'm going to do. I'm going to query sales by category here. So query to get our top 10 customers. That's this one here, and this is the sales by category. And then I'm going to, let me show you that. Sales by category, K. Okay, so here's our categories, all 37 of them, and then their total sales. So here you can see road bikes has got 12 million in sales, and then mountain bikes has got 11,700,000 in sales. So what I'm going to do here is I'm going to create like a massive mountain bike order here. And that'll change the order we've got in our materialized view. Okay, so created that massive order. Now let's query for sales by category. And you can see in the change feed here, right? So here you can see mountain bikes now is our new top category for sales, and then road bikes is second. Okay. And let's just delete that. We'll send that back to normal again. And then you can see, and there's change feed update, and then query sales by category. And now you can see road bikes is top again. So that is just basically change feed again. So here's my change feed for that. And here I've got my database container customer, and then product, and then sales by category. So in this one here, I'm keeping an eye on my customer container, checking for type sales order, deserializing that, and then grabbing all of the products out of that order. And then for each one, I'm going to update category sales by passing in the SKU and the sales amount in here. So update category sales in here. And I'm going to run this query here against the product table. Because here's the trick is I don't have category in my sales order table. So I could make this even more efficient if I actually pass the product category with each of the order items in that, so I don't have to go back to querying product table here to get the category, because that's what I have to do is I have to query the product table by the SKU, which by the way is a cross-partition query, to get the category name in there, and then I can go and then update category sales in there with that. Okay, so that's that one there, and let's go back to slides. Okay, so we're nearly at the end of remodeling our database here. And so far, we've created the following containers to support our design for our e-commerce application. We have a customers container, which supports both customer and sales orders. We have a product container, which supports or contains all of our product items in there. And then we have a product tag container and then a product category container. But there's one more optimization we can make further. Notice that both product tag and product category share the same partition key. And as you may have guessed, because they share that same partition key, we can just group them together in the same container, which we can rename to product meta. Now we can use queries like these to get all of our product categories and product tags. In fact, this pattern works for any kind of master or reference data you need to maintain, which is why adding that separate property should make more sense for you now that you've seen kind of our final design. So here's our final design, fully optimized. We've gone from 9 tables in our relational database to just 3 containers, and all of them optimized for our application, e-commerce application, to run at scale and do so efficiently. So that's kind of the end of my talk. Hopefully you've been able to see and learn some techniques for how do you model data in a database like Cosmos DB. Just some more good stuff for you I wanted to pass your way. All of the demos you saw are all in GitHub. So if you go to github.com/AzureCosmosDB/CosmicWorks, you can get a link to all of that and the sample data. There's also a great article, aka ms/practicalcosmosdb. This is a good article that shows how to model a blog platform on YouTube/AzureCosmosDB, a bunch of awesome videos. And then gotcosmos.com is just a great link of a bunch of aggregates, or a link aggregator of a bunch of content. Next, I also wanted to point out, we're doing a live conference on April 20 through the 21st. So if you go to gotcosmos.com/conf, you can learn more. You can add a calendar thing to your email. Here, I'll show you. So go to Azure or gotcosmos.com/conf and learn more. We're going to run 3 3-hour live segments with content from people around the world, customers and Microsoft folks. So should be great. You'll get to see real people running real applications and talking to you about what they learned on there. And then you can add each of these to your calendar in there. You can also just RSVP by email if you want. And that's it. Ready for questions, I guess.
Yes, thank you, Mark, for a presentation. I might say also, if I'm not working with this service now, I understand it much more what I was learning for the previous exams. So it was a great
Good.
show.
Well, I'm hopefully people understand, right? I mean, the reason you use a service like this is typically for high availability. I mean, that's kind of one of the benefits of being a distributed NoSQL data store we can survive regional outages better than you can, say, a relational database. And we can also provide guaranteed low latency. In fact, we're the only database in Azure that has an SLA on latency. And we're the only database in Azure that has a 5 nines availability guarantee when you run in 2 or more regions. So that's why, customers that have needs where they need to keep their database up, or they need high performance and greater scale, typically we'll turn to a database like this, because when you have a scale out model, you can grow to an unlimited size. And if you partition your data correctly, you're going to get the same latency, whether you've got a megabyte of data in there or a petabyte of data in your database. So that's not something you can do with a relational data store, because they're scale up and they can only scale so far in there. So
we do have 2 questions in the chat. The first
Sure.
one is, should I always create the partition key in my collection in Cosmos DB? What if I create the partition key for ID and then I also need to query the collection by name, for example?
Right. So the answer, 2 questions. Should I always create a partition key? Yes, you should always create a partition key. Even for small data like the product category and product tags, I still created a partition key. In this scenario here, I did it because it allowed me to I can put different types of data into that container and just store it more efficiently. Also, the fewer containers you have, the less throughput you need as well. So it's more efficient that way. Now, if you frequently query by name, then, I mean, there's 2 ways to look at it. How do I put this easily? It depends, right? If you frequently query by name, then maybe you should use that as a partition key within your application. It really just depends. The key here, and why I showed you at the beginning in the portal, is you want to measure the throughput. And then if it's less expensive to run change feed to push that data into another container. Well, let me back up. If you have 2 queries and they both are run a lot on that, say you have a query, you're querying customers by their name, and then another one where you're querying customers by say zip code or state or postal code or whatever. If you need to run those queries a lot, what you can do is use change feed to maintain essentially a materialized view of both. One partitioned by name and the other one partitioned by postal code. That way you can run high volume queries and always keep them in partition and efficient within there. Doubling data or duplicating data in a NoSQL database doesn't matter, because you're not optimizing for storage, right? In a relational database, the whole point of normalizing data is to reduce storage consumption, right? That's why you're always reducing duplicate of data. In a NoSQL database, it doesn't matter. Storage is cheap now. What's really expensive is compute. So if I have to go back and make lots and lots of requests to go get my data, that's going to cost a lot of money, and it's not scalable either.
Absolutely.
So just be comfortable with duplicating data and then using change feed to maintain the different copies.
Okay, and the second last question is there any smart tool for Cosmos DB, similar to Database Engine Tuning Advisor in the SQL Server?
In our portal, we actually have an indexing advisor that appears when you go into your Cosmos DB blade. So we are building tools that, or at least productionalizing tools to help make that easier for you, so you know if you have a good indexing policy. We're also working on a partition key advisor as well that should help with customers as they're working on designing. This will also appear in the portal as well and just show up as a little toast when you're in the Cosmos DB blade in there. So So we're working on tools like that. I have to say that the state of the art, if you will, for NoSQL databases is not as advanced, if you will, in terms of having the luxury of lots of tools and stuff. Relational databases have been around for 50 years, and you have 50 years of computer scientists and engineers and folks designing and improving query engines and tooling and stuff like that. This type of database has only been around for 10 years. I mean, it really kind of started back in about 2010 with Mongo. That's kind of the first commercially available NoSQL database. So hasn't been around as long, but we are working on making that easier for customers because, frankly, it can be a bit of a challenge designing a database for an application because you really need to understand fully. You have to understand the application and all of its access patterns and how the application is going to be used so that you can design an efficient data model for Cosmos.
Yes. Okay, I believe that's all. Once again, thank you very much for joining and presenting in Azure Saturday Belgrade Conference. Mark, I wish you a nice rest of the day. And for the rest of the viewers, I would like to call you to join us in the track 1 for closing of today's conference.
Great. Thank you very much.